All right, welcome back. So we're going to talk about how the electrical signals will actually travel through the heart. So I'm going to hide me and we'll get going. All right, so what you're seeing here is sort of a computer-generated mock-up of what heart muscle cells actually look like. So they have this kind of branched pattern, and you see there are these little junctions. So this branching gives them what they call a stair-step appearance. And these junctions are what are known as intercalated discs. So these intercalated discs, and this will kind of bring you back again to 201, contain desmosomes. And if you remember, those are those junctions that hold fibers together. They're kind of like spot welds, as well as gap junctions. If you remember about gap junctions, they're going to allow ions to flow in, or I should say, through the cell membranes of different cells. So what that means is that signals can very quickly go from one cell to another in a very fluid-like manner. Again, very important so that these skeletal muscle cells can contract in a very choreographed manner. They're striated. If you kind of remember back, if you remember back to 201, meaning that they have actin and myosin in them, very similar to skeletal muscles. Okay. Other things, they're autorhythmic, meaning that they're self-excitable. So basically, so you, I guess, theoretically could go and reach into someone's chest, pluck out their heart, and it would still stay beating. It's one of the nice things. That's one thing's why you're able to actually do heart transplants, for example. You can simply stimulate the heart muscle cells again, and they'll start, plugging away at their own pace. These cells have their own pacemaker, so there is a set beat that they go to, and again, they form this conduction system. So let's just take a quick look at that conduction system. Everything is going to start here in the upper wall of the right atrium. Okay. That spot where everything starts is something called the sinoatrial node, or the SA node. That's where the electrical signals start, and they spread over toward the left atrium as well as down toward the ventricles. After the SA node, these signals will reach something called the atrioventricular node, so here by the border of the atrium and ventricles. Oops, let's see, come on. From there, they're going to travel down sort of the walls into the ventricles via this atrioventricular bundle, or the bundle of His, and then down that interventricular septum via the left and right bundle branches. And then they're going to split, and they're going to kind of come back up into the ventricles, into that trabeculae carneae, via things called the Purkinje fibers. So remember, this is the only way that the signal is going to spread, thanks to that fibrous skeleton in the heart. So signals start in this SA node. They travel. Again, they can only travel at very certain areas because of that fibrous skeleton acting as an insulator. They travel to that AV node, down the bundle of His, down those bundle branches, and then to basically into the trabeculae carneae via these Purkinje fibers. That SA node acts as a natural pacemaker, as this says. It actually is fairly fast. It will want to initiate heart contractions about 100 times a second. So basically your heart, if we let it do its thing, it would your heart would beat 100 times a minute. I should say a minute, not a second. Sorry, that's a typo. So 100 times, that's awfully fast, a minute. Okay. So left all by itself, your heart would want to beat 100 times a minute if we left it up to the SA node. Okay. You have nerves from the parasympathetic nervous system. Parasympathetic. Okay. That will modify this. So your normal resting heart rate is probably closer to about 70 beats a minute. Okay. Some athletes, it could be even lower than that. Okay. So again, nerve impulses from the parasympathetic nervous system actually modify that timing, and we'll talk about how different hormones can also modify the timing, as well as the strength of each heartbeat. So the nervous system helps moderate your heart rate, however, it does not establish the fundamental rhythm. That's what the job of the SA node is. All right, let's talk a little bit about action potentials and how we actually get like what it actually looks like in the heart if we're kind of hooking up to an EKG. So here's just a little flashback again to 201. Do you guys remember this? Where if you had a neuron, it's at a resting membrane potential of -70. Some stimulus comes in, causes it to hit threshold at -55. Sodium channels open up, you have depolarization. Sodium channels close, and then you have repolarization because of potassium channels. And then basically the potassium channels also close, and then you have this little bit of hyperpolarizing, and then finally back to a resting membrane potential. Okay, so we have something very similar to this in the heart, but we have something, this middle stage that we do not see in neurons called the plateau. Okay, so again, and we're also at a little bit lower resting membrane potential, so we're at a -90 degree, or 90 degrees, 90 millivolts rather, -90 millivolts. Again, you have that signal coming in, and then you have rapid depolarization due to those voltage-gated sodium channels opening. But we have this plateau, okay? And what ends up happening is we have a third channel that we didn't have in neurons, and that's a calcium channel, okay? So it's basically, you have voltage-gated calcium channels now that are also going to open, and as potassium is flowing out, some of the calcium is flowing in. So basically we don't see that repolarization until the calcium channels finally close and potassium leaves the heart, okay? And then we get repolarization, right? So again, we have the actual depolarization due to the voltage-gated sodium channels opening, just like we've always seen. But then we end up having this plateau because we have a third voltage-gated ion channel, which is a calcium channel, allowing calcium in at the same time that potassium is leaving. So we have sort of this status quo. It's not going up, it's not going down, it's just being maintained until finally the calcium channels close, and then the potassium is able to leak out and we repolarize. Okay. Also kind of color-coded down here, in green is the time where we have what's known as depolarization, red is repolarization. I think that's kind of obvious. But during this time we have a refractory period, meaning that we cannot get another muscle contraction to occur during this time period. Okay, and that is going to be really important. You do not want to have a situation where you could possibly have tetanus in your heart because you would die. You have to have it always contracting. So this refractory period is very important, particularly in the heart. All right, so basically what does an EKG look like, right? We'll see that in lab as well. Depending on how you spell it, whether or not you spell it electrocardiogram, so ECG, or the more European German way of EKG, electrocardiogram with a K, you'll see it written either one of two ways. But basically, you can see this, it's a record of the action potentials produced by all the heart muscle fibers. So what we just saw a second ago, that was like one muscle fiber. This is like all of them, okay? And basically what you're doing, you're going to compare the readings from different leads. In lab, we're only doing 4 leads. If you go and get your heart tested, sometimes it's like 12 leads, if not even more leads than that. All right. Hopefully you can kind of see, here we're at 0 millivolts. We get this little P wave, first little peak, and then you'll notice that's followed by an atrial contraction. Then we have this little dip, that's the Q, big peak, that's the R, back down to the S, and then it's actually a little bit shortly after that, so it should probably start a little bit here. We have ventricular contraction, and then we see this other kind of more, I don't know, gentle kind of peak, the T wave, right? So this is our EKG. These are our recognizable waves, the P, the QRS wave, and then the T wave. All right, let me just kind of back up before I get there. What we're seeing here in the P, this is the electrical signal that's occurring here. So again, we have the electrical signal and it tells the atria to contract. The atria is contracting. Then we have the signal, it's going down those that bundle of His, those left-right bundle branches, it's getting to the Purkinje fibers, and now we have ventricular contraction. Okay. What you're seeing here in this T wave is basically ventricular repolarization. So basically the ventricle is going to relax. You don't see that in the atria because that signal is right here and simply masked by this enormous QRS wave. All right, we'll cover this in lab, but I want to go over this with you quickly here in lecture in case you have any questions. All right, so what you're going to be looking at, particularly in lab, is you'll see you have different readouts. And we're going to look for the one that's on lead 1. Okay. And what we're going to look for, hopefully you can notice, you can see this, there's these darker pink lines and these lighter pink lines, right? So what you're going to do is you're going to, for basic, let's see if I can get my pen to work. You're going to look for the line that is as close to being on one of these dark pink lines as possible. So this QRS wave right here is almost right on it. So we'll start with this one. So what we're going to do is the next dark line, next dark pink line, we're going to label that one 300. Okay? And then the next dark pink line after that, we're going to label that 150. Okay? The next pink line after that, we're going to, like dark pink line, we're going to label that 100. The next one after that, we're going to label 75. And then the one after that, we're going to label 60. Okay? And where I'm getting these numbers from is this very first one. We start with 300. That's basically divided by 1 is 300. 300 divided by 2 is 150. 300 divided by 3 is 100. 300 divided by 4 is 75. 300 divided by 5 is 60. And you'd keep going, so on and so on. Does that make sense, hopefully? And you only have to keep going until you bracket another QRS. So I stopped here because now I've got a QRS between the 75 and 60. So what I can see just by this is that I know that my heart rate is somewhere between 75 beats a minute and 60 beats a minute. And just by eyeballing it, I can see that it's going to be somewhere closer to 75 than it is 60, right? Hopefully that makes sense to you too. All right. Now if we look, so we need to figure out exactly how many, okay? Well, luckily we have these little boxes, these little pink lines. So we have, let's see, I have 1, 2, 3, 4, and then basically there's 5 lines between these two. So there's 5 sort of division points between 60 and 75, right? So if we simply subtract the two, 75 minus 60, I should say, we get 15, right? Hopefully that makes sense. 75 minus 60 is 15. So the value between these two is 15 something, right? So then again, we said we had 5 boxes. So each box, so we just divide, 15 divided by 5 is equal to 3, right? So now we know each box is worth 3. So we have 60, 63, 66, 69, what's the next? 72, right? And so we're somewhere between 79 and 62, so maybe 69, 72, so maybe, I don't know, 71-ish, or about 71. So our heart rate would be 71 beats per minute, right? Hopefully that made sense to you guys. If this does not make sense to you, please let me know and I'll be more than happy to go over it with you again. Okay. Come on, slide. All right. So we've already kind of seen this. This is just sort of what I was telling you guys about those EKGs and words. So this term systole means contraction. The term diastole means relaxation. So basically, we have the SA node, a signal starting to fire. We see the P wave. Then the atria contract. In other words, we're seeing atrial systole. Okay? Then that signal gets sent from the SA node, and it enters into that AV bundle, and then out over the ventricles, we see that QRS complex, right? We do not see atrial repolarization, as I mentioned, because this QRS complex is just too large. It masks it. Okay. Again, we have ventricular contraction or ventricular systole. Again, it begins shortly after that QRS complex appears, and it occurs. It keeps going until we hit that T wave. Once you see that T wave, we have repolarization of the ventricle fibers, and afterwards the ventricles relax. Right? We have diastole. So if we kind of look at this again in a slightly different way, So again, we see action potential in the SA node. We start seeing the P wave. You see the green there. The atria contract. So the atria are contracting. Then we have the QRS, and you can kind of see where the nerve signal is. Then the ventricles are contracting, right, in that period. The ventricles start to relax during the T wave, and then everything's kind of back to normal. All right. Here's a video if you need to watch, if you'd like to watch this in like video format. Okay. When we talk about a cardiac cycle, we're talking about all the things that are, that's just what we just talked about. So it's all the things that are going on in one heartbeat. So the contraction, the systole, and the diastole of the atria and ventricles. The contraction, relaxation of the atria and ventricles. Okay, again, each cycle, the atria will contract, the ventricles are relaxed, then the atria relax, the ventricles contract, so they alternate contracting and relaxing. Okay, again, we're pushing blood from where it's high pressure to low pressure. All that means is as the ventricles are contracting, pressure increases, and it gets like pumped out the aorta or the pulmonary trunk. It goes towards less pressure. Okay, and again, you saw this brief relaxation period where both the atria and the ventricles are relaxed. You probably have gone to a doctor and they put the stethoscope up to your chest to listen to your heart. And they're never like right on your heart, right? They're actually like a little bit off to the side. And when they're listening for heart sounds, that technique is called auscultation. So that technique of listening to the body for, trying to diagnose via sound is auscultation. And the sound that they're listening for is actually due to the turbulence of the blood when the heart valves close. So basically the blood kind of swirling around because it's kind of bouncing off those valves. Okay, so you probably heard that, your heart kind of sounds like a lub-dub, 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 right? So that lub are the atrioventricular valves closing, okay? So the tricuspid, bicuspid valve. And then the dub are the semilunar valves closing, or the aortic and the pulmonary valve. All right, that tends to be quite a bit of information. So again, please let me know if you have any kind of problems calculating heart rate or any of those other calculations. I'm more than happy to help you. Let me know if you have any questions about EKGs or the conduction of the electrical signal to the heart. I'm more than happy to answer any questions. All right, I'll see you next time.